Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, how do you control the microrobot? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week I'm finding out more about microrobots and how roboticists are addressing the unique challenge that their small size presents. Before that, I'd like to remind you that you can contribute to the conversation by sending in questions for my future guests. I announce upcoming guests on social media and Patreon, so make sure you follow the podcast to find out what's coming up. You can submit questions on the website at robottalk.org, on Patreon at patreon.com/Claire Asher, or by replying to one of my guest announcements on social media at Robot Talk Pod. So, without further ado, let's get on with this week's interview. I recently had a fascinating discussion with Ali K. Hoshiar from the University of Essex about how microrobots move and work together. Today, I'm talking to Ali K. Hoshiar, a senior lecturer at the University of Essex, working on soft, microscale robots for medical and agri-tech applications. Hi Al, welcome to Robot Talk.
Hi, thank you. It's a pleasure to be here.
So you're the director of the RUMI lab at the University of Essex, which stands for Robotics for Under Millimetre Innovation. So can you give us a little bit of an overview of the research that's going on at RUMI?
Sure, of course. So, as you mentioned, in my lab, Robotics for Under Millimetre Innovation, we are working with tiny robots smaller than human hair. And we are developing these robots for different applications. So, mostly for medical applications, but we are also working on some environmental applications as well. Mm-hmm. We also develop slightly larger robots, soft robots for different applications as well. But our main focus in RUMI is small-scale robotic, microscale robotic for medical applications.
Fantastic. Microrobotics is a topic we've covered briefly, like a couple of times on the podcast before, but it's something that people can find is quite hard to get their head around, right? You know, you think of a robot vacuum cleaner, you can picture that. It's a thing you can pick up, you can touch. Maybe it would be helpful to kind of talk a little bit about what these microscale robots are like, what they're made of, try and build up a picture in our minds.
Sure. Basically, in my field, in microrobotic field, whenever we want to start talking about microrobots, we go back about 60 years and we start talking about Fantastic Voyage. So Fantastic Voyage was this movie which was made in 60s. And the idea of the movie was, can we miniaturize the submarine, inject the submarine to vascular network, and then the submarine goes to the brain and open a blood clot. So that was the idea in the movie. And the whole development in early 21st century, it started developing this field. So back in 2010, we started to be able to control very precisely magnetic field using some magnetic actuation systems. Okay. And then we started to develop miniaturized devices using 3D printers. So that combination of these two technology development made the Fantastic Voyage reality. So now we can develop miniaturized devices the size of the submarine on that Fantastic Voyage story. And then we can very precisely control them through electromagnetic field.
Okay. So what are they made of? You mentioned 3D printing. I think usually I imagine 3D printing with plastics, but they're not magnetic.
So there is a technique called two-photon polymerization. So they use that technique, and they are made of different sorts of resins. So there is a very wide range of research ongoing about how they are manufactured or they are fabricated. And nowadays, it's mostly about biocompatibility, and they are made of biodegradable material. So the field evolved on that area, but they also need to have a source of magnetic properties so we can control them if we are controlling them magnetically, because there are other ways as well.
Okay. That leads quite nicely into what I wanted to ask you about controlling these robots. So, you can't control a micro-scale robot in the same way you would a larger robot. So you've obviously mentioned that you use magnetic fields. Do you want to elaborate a bit on how you make these robots move?
Yes, of course. So, we need to consider two things, especially when we are talking about microrobots. The big change is the physics. So, when we are talking about small objects, the physics involved is very much different, because the forces involved are different. Because when we go to the smaller scales, the surface forces are more dominant compared to volume forces. And especially if you want them to swim, whole physics around that is changing. So you can consider that you are swimming in a pool of honey. And that is the feeling when a microrobot is moving at that small scale. So one thing to consider is the physics. The other thing is that how to actuate them, how to actually make them move.
Yeah.
And obviously we have a very small object, so we cannot have things like batteries and motors on them.
Yeah.
So first of all, swimming mechanism is different compared to the larger scale. And the second thing is the way that you empower them is different. So the power source should be remote. So we should remotely make them to move. And one way that we can do that is through the magnetic field. So through the magnetic field, we can have systems, and many of them are already commercialized. And we have electromagnetic systems, and we have also robotically controlled magnetic field through the permanent magnets. And through this magnetic field, now you can rotate your magnetic field and make them swim, or you can actually pull them through the gradient field, and you can actually make them to move or to behave in a certain way. In order to control, if you control your magnetic field, remotely you are controlling your object.
So do they have like moving parts, or is it like the whole micro robot is moving as one object?
Yeah, there are different mechanisms, but the most popular one is the whole macro robot is actually moving. And there are actually different type of them. So initially they were like cylinder type or a spherical type. But the most efficient one is the helical type. So helical type robots are like actually from helical shape and
like a screw.
Yeah, like a screw. So by rotating the magnetic field, and as I mentioned, it's like swimming in the pool of honey. So you can actually imagine that's how they move forwards.
Okay, they're almost like drilling through the liquid. Okay.
So that's actually physics behind it.
And I mean, you've mentioned them swimming through blood vessels. Obviously, our heart is also pumping blood around. So if they're moving in the direction the blood is moving in, that would kind of push them along a bit. But if you wanted to go against the flow, that's going to be even harder.
Yeah, I agree. So that would be one of the challenges that we need to answer in microrobotic field, and that's an open challenge, because most of the research so far has been done under the no-flow condition, under lab experiments. Nowadays, the field is evolving, so stronger magnetic fields and the stronger electromagnetic systems, which are now in the human scale. And some researchers started doing research on big animals to answer these questions. But so far, most of the research has been under no-flow condition.
Yeah.
But yeah, that's one of the key issues that we need to solve if we want to move to more practical applications.
Sure. And yeah, obviously, because of their small size, microrobots maybe can't often achieve very much individually, but one of their advantages is that you can kind of deploy large numbers of them to work collectively on a task. But then if you're using magnets to control them, then they would presumably all respond to the magnetic field at the same time. I know this is a challenge you've been working on addressing in a project called In-Target. So could you tell us a bit about that project?
So, yeah, as you mentioned, microrobots are very tiny. It's like the diameter of human hair. So they cannot carry much drug, or they cannot have much impact if you are going to use them individually. There are some applications, but at the end, you need to control them collectively. And as you mentioned very clearly, if you are collectively controlling them, all these microrobots are receiving the same sort of control signal through the magnetic field. And that makes it very difficult. So let me give you an example on how this works. So you can consider an orchestra and a director in the orchestra, right? So you can consider everyone is receiving the same signal to do something, but the instruments are different. So the sound coming from those instruments are different. So this is one aspect. So you can make those microrobots individually slightly different. So they behave differently through the same signal. Or sometimes some of them are receiving a different signal from the director than the others. So they are going to do something slightly different. So that's the same way with our approach. So what we are trying to do is we are trying to study their collective behavior. So how we can actually combine them, and how we can move them, and how we can actually make them disperse when they are reaching to some destination. Also, we are working on the magnetic field itself, how we can actually make the magnetic field specialized, or we can actually make it tailored for some specific design through use of AI, machine learning, and these sort of techniques.
Fascinating. It really requires quite a lot of lateral thinking, this field of research. Yeah, another aspect I wanted to talk to you about was kind of sensing. So obviously, we classically think of robots as sensing and responding to the environment around them, but at this scale, cameras, LiDAR sensors, all of the stuff that normal robots have just doesn't work. So how do you approach sensing for microrobots?
Yes, basically, we cannot have onboard sensing, as you mentioned, because of the size of these microrobots are very tiny, so we cannot attach any sort of sensors. So what we do is, usually in the field, we use external monitoring system. Things like, depending on the applications and depending on the level that actually your current development is. So you can use cameras, or you can use X-ray, ultrasound, and these sorts of techniques to monitor their movement. In a sense, the robot itself became your sensor. The shape of the robot, especially if they are shape-forming robots, became your sensor. From the behavior of the robot, you would understand the signal, and then you can control them.
Okay. So talk me through what you imagine, this whole process would look like in the future. So imagining that I need some kind of drug delivered to a part of my body, and you're, going to use microrobots to do that. What would the process be like?
So we are currently not there. So microrobots, they are evolving. So I would say in the next 5 years, you will see some of them are reaching to the level, clinical level. I know some people are using it preclinically, but we are not quite there. So it would be an imaginary situation in the future. But basically, what I can imagine in the future about the microrobots is that they will be injected relatively close to where they are supposed to go, so to the target area in the body. And then after that, they will be exposed to external magnetic field and some sort of control. And it would be very useful, because then you can target exactly where you need it. And then they will be dispersed to a tumor, or they will be actually used for this sort of application. But we are mostly talking about untethered microrobots. But there is another field that I'm also very interested in, and that's tethered microrobots. Tethered microrobots are very small microrobots, very much similar to human hair, and they can be connected to already available conventional tools like guide wire and catheter. And what you can do is, now, instead of manually moving these devices, you can actually develop a robotic system. And interestingly, this actually gives a huge advantage, because at the tip of these guide wires and catheters, now you have an active material that you can put it into different shapes. And you can control them more precisely to go and do the conventional tasks they currently do.
Yeah, that's really interesting. I have never heard about that. I guess there's two things that you've mentioned that we haven't covered yet. The first was about larger scale soft robots that you're working on. So do you want to tell us a little bit about that?
Yes. So in my lab, because we are interested in soft robotic as well as microrobotic, and I've worked on a range of different things. So one of them used to be soft magnetic robots, so magnetic small scale robots, which are made of soft material. And they are actually they are magnetic particles, or mostly neodymium particles, in their body, and then you can put them into different shapes, and then you can control them. So it started from there. But then I've got interested in soft growing robots. So we had done a very small project on one application. So it was supported by EPSRC. So we had a very small actual project on this soft growing robot, which could be used for agricultural applications. So what I thought at the time was robots are very precise for agricultural applications and very expensive. So why we are not developing this sort of technology for agricultural applications? And we started developing soft growing robots. Okay.
What kind of uses in agriculture would the soft growing robot have?
We thought about monitoring, because in East England, there are lots of farming, and there are lots of actually industrial farming in here. And we thought for monitoring, we can use this sort of technology that constantly can actually grow and constantly can monitor through cameras, and then can report it back. And we can have this application for soft growing robots.
Okay. I know you mentioned you're also applying your microscale robots to agri-tech applications. So what kinds of applications?
One of the areas that I'm interested is especially for environmental monitoring. So it is underexplored, and is very interesting idea to use this sort of microrobotic technology for environmental applications, because we are mostly focused on healthcare application for a good reason. But I'm also interested on developing these microrobots further, especially for agricultural or environmental applications.
I mean, this is a little bit out there, but I mean, obviously plants don't have like a vascular system like we do, but they do have, water and nutrients flowing through them. I wonder if one day you might be able to inject your microscale robots in to treat disease or something like that.
Yeah, it would be very difficult. And then, I mean, as you know, usually in robotics, we need to also think about the cost of the process like this,
That's
right?
True.
So it would be too expensive.
Yeah, fair enough. I can dream. Al, it's been fascinating chatting to you today. I've been speaking to Ali K. Hoshiar from the University of Essex. Thanks, Al.
Thank you. Thank you.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. And don't forget to join the Robot Talk community on Patreon if you'd like to support the podcast and get access to some awesome perks, including monthly bonus episodes, behind-the-scenes updates, and more. Visit patreon.com/Claire Asher and join the Robot Talk community today. Next week, I'm chatting to Yuan Ting Chan from the Natural History Museum about automating museum experiments. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.